Hello. It's a rainy Saturday. Gotta go to the airport. But I'm gonna start listening to the ABCs of Relativity. This is my reading the cover. I know a little bit about relativity. I know what it means. I know it's about movement of light and how time is relative to the speed you're going because there's some kind of influx of mass. That's what I know of, but that's about it. Enough to impress a fourth grader, but that's about it. Yeah, I need to know more. So let's see how much more intelligent I become. All this stuff. I finally listened to all of Bertrand Russell's book. I actually finished listening to it maybe a week ago, but I've been waiting on some camera gear and all that stuff so I could look a lot nicer, and my computer's fighting me right now, so I was just like, screw it. This is the first video, it doesn't have to be perfect. I think seeing the evolution of the videos I make is gonna be pretty good. I kind of just jumped into it, and the next one I do will be much better, much more organized. So, I apologize, this one seems a little bit janky. I was able to digest the book and I'm gonna break it down for you. So, the first thing I wanna do is, I think the author maybe didn't organize all of the ideas in the best way to convey the idea, or maybe this is just a more bite-sized way of kind of putting it. One thing that Bertrand Russell talked about is, why should we focus on things that are so abstract like relativity? How is this going to help us anyway? And he has a really good analogy that kind of breaks this down.
To the non-mathematical mind, the abstract character of our physical knowledge may seem unsatisfactory. From an artistic or imaginative point of view, it is perhaps regrettable, but from a practical point of view, it is of no consequence. Abstraction, difficult as it is the source of practical power. A financier whose dealings with the world are more abstract than those of any other practical person is also more powerful than any other practical person. Financiers can deal in wheat or cotton without needing ever to have seen either. All they need to know is whether the price will go up or down. This is abstract mathematical knowledge, at least as compared to the knowledge of the agriculturist. Similarly, the physicist, who knows nothing of matter except certain laws of its movements, nevertheless knows enough to be able to manipulate it. After working through whole strings of equations, in which the symbols stand for things whose intrinsic nature can never be known to us, the physicist arrives at last at a result which can be interpreted in terms of our own perceptions and utilized to bring about desired effects in our own lives.
Now I am become death, the destroyer of worlds.
One thing that I found that was quite interesting in my opinion is that it seems that so much of our math and what we understand is based on Pythagoras, the a squared plus b squared equals c squared guy. You know, that's like the one thing I remember from math class, and he's actually like really important, has an interesting history, which Bertrand Russell describes.
However, it is necessary first to explain a certain amount of history, and for this purpose we must go back as far as Pythagoras. Pythagoras was roughly a contemporary of Confucius and Buddha. He founded a religious sect which thought it wicked to eat beans, and a school of mathematicians who took a particular interest in right-angled triangles. The theorem of Pythagoras, the 47th proposition of Euclid, states that the sum of the squares on the two shorter sides of a right-angled triangle is equal to the square on the side opposite the right angle. No proposition in the whole of mathematics has had such a distinguished history. We learn to, quotes, prove it at school. In fact, the proposition is not quite true. It is only approximately true. But everything in geometry and subsequently in physics has been derived from it by successive generalizations. One of these generalizations is the general theory of relativity.
So the idea of relativity and things having a kind of a relation to each other that kind of boggles the mind when you're basing it on human senses goes way before Einstein. Actually, there was an observation made about dropping a weight on a boat.
A very similar difficulty was explained by Galileo at the very beginning of modern physics. Most people think that if you let a weight drop, it will fall vertically. But if you try the experiment in the cabin of a moving ship, the weight falls in relation to the cabin, just as if the ship were at rest. For instance, if it starts from the middle of the ceiling, it will drop onto the middle of the floor. That is to say, from the point of view of an observer on the shore, it does not fall vertically, since it shares the motion of the ship. So long as the ship's motion is steady, everything goes on inside the ship as if the ship were not moving. In orthodox physics, which is derived from Galileo, a uniform motion in a straight line has no discoverable effects. This was, in its day, as astonishing a form of relativity as that of Einstein is to us.
So now on to Einstein, who a big majority of this book is devoted to. It took Einstein a long time, like decades and decades, to actually figure this out.
This was the plain and natural meaning of the experiments, and Einstein succeeded in inventing a theory which accepted it. But at first it was thought logically impossible to accept this plain and natural meaning. An analogy will make it clear how very odd the facts are. If you are on an escalator, you reach the top sooner if you walk up than if you stand still. But if the escalator moved with the velocity of light, you would reach the top at exactly the same moment, whether you walked up or stood still.
One way of looking at this entire thing that I think a lot of people don't see, I mean, the idea of space-time, we have XYZ for finding your area in space, but there's also another dimension in there, which is time.
And we assume that in order to assign the position of an event in space-time, 4 quantities, coordinates, are necessary. Taking, for example, our explosion on an aircraft, they are latitude, longitude, altitude, and time.
One thing I wasn't aware of before is there are 2 different kinds of relativity. I thought the names were, interchangeable, but actually they are 2 different kinds. One is for an object that's in isolation in deep space, and the other one is basically for everything else when there's even a planet that's light years away, or a sun, or a black hole that can have an effect on any mass at great distances.
There are 2 forms of the theory of relativity, the special and the general. Special is used in the sense of limited to special circumstances. It is, in most circumstances, only approximate, but becomes very nearly exact at great distances from gravitating matter. That came first. Einstein later developed the wider general theory, which can cope with gravitational matter. Whenever gravitation may be neglected, the special theory can be applied, and then the interval between 2 events can be calculated, when we know that distance in space and the distance in time between them, estimated by any observer. The special theory lets us describe one interval in space-time, that is, space-time, which replaces the 2 intervals in space and time of the older physics.
So one thing to kind of understand the overall perspective of this is to understand geodesics. It's the idea of when you're flying, from, let's say, the west to the east, from the US to Asia. You don't fly in a straight line over the Pacific. You fly all the way over Alaska and over Japan if you're trying to get to Taiwan or China or something. And this is because the Earth is curved. Well, space is also curved in a sense, curved with time and in ways that we can't really completely comprehend, or you have to be like an amazing mathematician to do it. But throughout the book, he talks about geodesics a lot because it's a really good frame of reference for understanding this kind of really abstract idea of how time is wrapped in with space.
Suppose you try this on the Earth. Walk 100 kilometers west, then 100 kilometers north, then east, then south. You might think this would make a square, but it wouldn't, because you would not come back to your starting point. When you are nearer the pole, 100 kilometers takes you through more longitude than when you are nearer the equator, so that in doing your 100 kilometers east, if you are in the northern hemisphere, you get to a point further east than that from which you started. As you walk due south after this, you remain further east than your starting point, and end up at a different place from that in which you began. In a sense, what we have just been saying is not quite fair, because, except on the equator, travelling due east is not the shortest route from a place to another place due east of it. A ship travelling, say, from New York to Lisbon, which is nearly due east, will start by going a certain distance northward. It will sail on a great circle, that is to say, a circle whose centre is the centre of the earth. This is the nearest approach to a straight line that can be drawn on the surface of the earth. Meridians of longitude are great circles, and so is the equator, but the other parallels of latitude are not.
So here's one that I kind of knew pretty well, but he has an amazing analogy. So this is the way that when you're getting really close to the speed of light, which is like that speed limit of all reality, at least that we know of, that things start to happen that are kind of strange, that in a sense are trying to slow you down, or how your perception of what's happening is relative to someone going at different speed. And he does this by breaking down an analogy of a train traveling, and the people in the train and the observers of this train that's traveling almost the speed of light.
You are in a train on a long straight railway and travelling at a significant fraction of the speed of light, say 3/5. You measure the length of your train and find that it is 100 meters. Suppose that the people who catch a glimpse of you as you pass succeed in taking observations which enable them to calculate the length of your train. If they do their work correctly, they will find that it is only 80 meters long. Everything in the train will seem to them shorter in the direction of the train than it does to you. Dinner plates, which you see as ordinary circular plates, will look to the outsider as if they were oval. They will seem only 4/5 as broad in the direction in which the train is moving as in the direction of the breadth of the train. And all this is reciprocal. Suppose you see out of the window a fishing rod, carried by someone who measures it to be 5 meters long. If it is held upright, you will also see it to be 5 meters long. But if it is pointed along the railway, it will seem to you to be only 4 meters long. In describing what is seen, I have assumed that everyone makes due allowances for perspective. All the lengths of objects in the train will be diminished by 20% in the direction of motion for people outside, and so will those of objects outside for you in the train. But the effects in regard to time are even more strange. This matter was explained with almost ideal lucidity by Eddington, and my example is based on one given by him. Imagine a spacecraft which moves away from the Earth at a speed of 250,000 kilometers a second. If you were able to observe the people in the spacecraft, you would infer that they were unusually slow in their movements, and other events in the vehicle will be similarly retarded.
Cute. Your sister's boss gave me a microscope that would have made me retarded.
Oh boy, Rick, I don't think you're allowed to say that word, you know?
Morty, I'm not disparaging the differently abled. I'm stating the fact that if I had used this microscope, it would have made me mentally retarded.
Okay, yeah, but I don't think it's about logic, Rick. I think the word has just become a symbolic issue for powerful groups that feel like they're doing the right thing.
Well, that's retarded.
Everything which took place there would seem to take twice as long as usual. I say infer deliberately. You would see a still more extravagant slowing down of time. But that is easily explained because the spacecraft is rapidly increasing its distance from you, and the light impressions take longer and longer to reach you. The more moderate retardation referred to remains after you have allowed for the time of transmission of light. But here reciprocity comes in, because from the point of view of the space travelers, you are moving away from them at 250,000 kilometers a second. And when they have made all allowances, they find that it is you who are sluggish.
Bertrand Russell did a very good job of helping me understand what gravity actually is. The way we use words to describe it kind of bastardizes the reality of what it is. And he has a really good analogy through explaining it like a bunch of people with torches on a hill.
As far as the geodesics are concerned, this has the effect that space-time is like a hilly countryside. In the neighborhood of a piece of matter, there is, as it were, a hill in space-time. This hill grows steeper and steeper as it gets nearer the top, like the neck of a bottle. It ends in a sheer precipice. Now, by the law of cosmic laziness, which we mentioned earlier, a body coming into the neighborhood of the hill will not attempt to go straight over the top, but will go round. This is the essence of Einstein's view of gravitation. What a body does, it does because of the nature of space-time in its own neighborhood, not because of some mysterious force emanating from a distant body. An analogy. Suppose that on a dark night, a number of people with lanterns are walking in various directions across a huge plain. And suppose that in one part of the plain there was a hill with a flaring beacon on the top. Our hill is to be such as we have described, growing steeper as it goes up and ending in a precipice. There are villages dotted about the plain, and the people with lanterns are walking to and from these various villages. Paths have been made, showing the easiest way from any one village to any other. These paths will be all more or less curved to avoid going too far up the hill. They will be more sharply curved when they pass near the top of the hill than when they keep some way off from it. Now suppose that you are observing all this from a balloon. You cannot see the ground, but only the lanterns and the beacon. You will not know that there is a hill, or that the beacon is at the top of it. You will see that the lanterns turn out of the straight course when they approach the beacon, and that the nearer they come, the more they turn aside. You will naturally attribute this to an effect of the beacon. You may think that it is exerting some force on the lantern. But if you wait for daylight, you will see the hill, and you will find that the beacon merely marks the top of the hill and does not influence the people with lanterns in any way. In this analogy, the beacon corresponds to the sun. The people with lanterns correspond to the planets and comets. The paths correspond to their orbits, and the coming of daylight corresponds to the coming of Einstein. Einstein says that the sun is at the top of a hill, only the hill is in space-time, not in space. Don't try to picture this. It is impossible to visualize.
One of the more amazing things that I found was I thought that physicists knew more. He puts it in a really good way, like physicists, we know a lot. Or not, I'm not part of those people, no way. The amount that they know and what they know is so ethereal, and it just makes me feel more like our reality is just, it's beyond us. We think of things as being, really solid, but in the end it's just kind of, is it a hologram? Is it a simulation? Is it an illusion? Is it a dream? I don't know, but when you go deeper into it, it slips through your fingers kind of, but we're trying. One of my more favorite things about this book was just at the beginning of the last chapter, the way he worded it, that in a sense there's a rhythm to the universe. It's almost like, I think he said verses in a song. And that kind of just really made me feel like I know there's some Hindu philosophies that describe the universe as like a cosmic song that's always repeating itself. So I thought it was interesting that Bertrand Russell, this English physicist, could kind of in a way bring this other perspective into it.
The world which the theory of relativity presents to our imagination is not so much a world of things in motion as a world of events. It is true that there are still particles which seem to persist, but these are really to be conceived as strings of connected events, like the successive notes of a song. It is events that are the stuff of relativity physics. Between two events which are not too remote from each other, there is, in the general theory as in the special theory, a measurable relation called interval, which appears to be the physical reality of which lapse of time and distance in space are two more or less confused representations. And it is upon these rules that the practical uses of physics depend. The final conclusion is that we know very little, and yet it is astonishing that we know so much, and still more astonishing that so little knowledge can give us so much power.